In this problem, we are given the diagram. And we want to find the reactions at A. And in this case, we want to know what's the tension in cable BC. I'll call that TBC. Now we want the free body diagram. We're back to static equilibrium. We need a free body diagram. But here we have, again, an object of interest. We're not looking at just a single particle. When you kind of go through a couple of these, get comfortable with it, the free body diagram step should be the difficult step. How are we modeling everything? What are all the orientations? Once your free body diagram is correct, the equations basically write themselves from the picture, and then it's just crunching numbers to solve those simultaneous equations. So this is really where you should be doing the most thinking, is on the free body diagram. The first thing, and this is, again, not always obvious, we have to choose what's the object we're going to isolate from everything it's connected to. So for this, what is the object of interest that we're going to free from all of its supports? The steel frame, we can choose that as our object, and what we're going to do is, again, free it from what it's connected to. It's connected to a pin at A. We're not going to draw the pin at A, but we're going to draw what the pin did to our steel frame. It's connected to a rope at B. We're not going to draw the rope, but we are going to draw what the rope does to our object. So our object that we're going to isolate is just this red steel frame here. That's our object of interest. I have my object. I now want to include the forces and the couples that act on my object. I tend to start with the applied forces, or these ones that are called out here. So like the 60 kilonewton force. And I'm just going to copy exactly this 30 kilonewton meter couple. So in the step of labeling forces, labeling moments, I've copied and labeled the applied couple, the applied moment. But now again, I have to include, because I did not draw the pin in my picture, I've separated it out. I have to put what did the pin do to the object that I kept. So this is a support, it's a pin support. This is where I think, because the pin is there, what does it prevent my object from doing, translation-wise and rotation-wise? So even though it was just on the previous page, we'll go through the thought process here. Because the pin is there, we ignore everything else that it might be connected to. But because of just the pin, can I move my steel frame left or right? It's attached to that pin. I can't just move it left or right. So there's going to be a force. Oops. I'll hold off for now. There's going to be a force preventing it moving left or right. Also, up or down, I can't just take my frame and move it up or down. But again, because it's attached to that pin at A. That pin prevents motion in the entire plane. I can represent that as components in the X and Y. I do have to establish a coordinate system, which I haven't done yet. I get to choose it. I'm going to choose X right, Y up, and Z towards us. For convenience, because that pin prevents all translation in the plane, I'm going to say it has an X component, I'll call AX, and a Y component, I'll call AY. And both of them act at where that pin would be. Right, so the pin is taken care of. Oh, it allows rotation around the pin there, so there's not going to be a couple from the pin. At point B, I have not drawn the rope. It's not in my picture, so I have to include what did the rope do to my steel frame. The rope, just like with a particle, can only pull, so I have to represent it with a tension. And I know, just like with a particle, that the tension in a rope acts along the direction of the rope. I'll call it TBC. It's pulling on my steel frame here. And I know that it's going in the direction, this 3, 4, 5 triangle. So I can represent its dimensions with the ratio triangle. I've included these lengths of these different segments. I have the angle of this force. AX is to the right, AY is up, so that's taken care of. So all of my dimensions are here. All of my forces, both external and from my reactions, are represented. I have my object, I have my right-handed coordinate system. So this would be my complete free body diagram for when my steel frame is my object of interest. With the free body diagram complete, I now can write my equations, my equilibrium equations. For the equation step, in 2D rigid body, I will take two sums of forces, x and y, and a sum of moments around a point I get to choose. The order you write the equations doesn't matter. They're all independent of each other. For right now, just out of habit, I usually do sum of forces x, then y, and then the moment. Although solving it by hand, that's not always the most convenient way to do it. But this way I don't kind of do the same step twice or skip a step. So I'll just start with sum of forces x out of habit, really. All right, so based on the coordinate system that I chose, I want to see all of the forces that have components in the x direction. I have all of AX, I said was pointing to the right. AY does not have anything in the x direction. I have my tension, TBC. A component of it is in the x direction, 3/5. And it points to the left, so it's going to be negative. My 60 kilonewtons is only in the y direction. So the entire point of the couple was, to simplify it, the couple never is included in the force equation. It does not contribute to the force, because if it came from two forces, they cancel each other out, so they're not included in the sum of forces. So equation 1 is done. This will not appear in any force equation. So I have AX, I have TBC. I have two equations, I have one equation, I have two unknowns. So right now I'm just going to put it aside, and I'll come back to it once I have more information. If I move on to summing forces in the y direction, I have all of AY pointing up. Again, I'll reiterate, when I drew AX and AY, I'm assuming AX is right, I'm assuming AY is up. I could be wrong, the math will tell me, and that's perfectly fine. But we have to choose some direction to start, so it's usually easiest or most convenient to just pick the one that goes in the positive sense of our coordinate system. So AY is up. I have a component 4/5 of TBC that's down. I have 60 kilonewtons that's down. And once again, the couple does not ever appear in our force equation. So from equation 2, I've introduced one more unknown, but only one more equation. I have two equations, but three unknowns right now. So again, for right now, I'll just put them both aside. I won't go to my solve step yet. I can't get anything numerically at the moment. So the new equation we get in rigid body equilibrium is I can take the sum of moments around any point I want, and it's going to equal 0. Looking at the picture, which point is probably going to make our lives the easiest if we take the moment around that point? Two forces have their line of action pass through A. Remember, any force that has a line of action pass through the point we want to take the moment about will have 0 moment contribution. So our goal here is, if we want to make our lives easier, write as little as possible, crunch as few numbers as possible. The more things we can eliminate from this equation, the better. So by choosing point A, AY and AX will not appear in this equation, which is good because it's less to write, but it's also good because then only one unknown is going to appear in this equation. And we can see by choosing A, the math becomes a lot easier to do by hand. Again, it's not wrong to choose B. It's not wrong to choose, let's call it C. But if I choose C, I'm going to have all three unknowns appearing in that equation. While not wrong, that's going to make this much tougher to solve by hand. If I choose point A, AX, AY don't have a contribution. If I look at, let's say, the 60 kilonewton force, what will the moment contribution be due to the 60 kilonewton force around point A? So it's a force of 60. What's the distance from point A? Right? And is it a positive or a negative moment around A? Right? So around point A, this is my distance, and it's creating a clockwise rotation around point A. Right? If I go to my tension BC, I want to see what is its moment contribution around point A. Like we saw in chapter 4, I probably want to break this up into its horizontal and vertical components. It's easier to find the distances that way. I'm going to start with the vertical component of TBC, which will be 4/5 TBC. If I'm talking about the vertical component of TBC, what is its distance from point A? Right? For the vertical component, it's 1. Then that would be my distance. And is that positive or negative around A? I also have the horizontal component around A that has a line of action that does not pass through A, so I need to include it. I will have the, I'll write it down here, 3/5 TBC is the force, and what is the horizontal component's distance from point A? Right, so these, the different components have different distances from A because they're oriented, one's vertical, but the other is horizontal. So again, for the horizontal one, I would be using that distance. Is this one positive or negative around A? Right, this one also positive. These can be of different signs as well. Don't think that they could both be positive. One can be positive or negative. So these can be different and the signs can be different. Finally, this is where I do include this couple, this twisting of 30 kilonewton meters. Right, so I'll have 30 kilonewton meters. We don't multiply it by anything. It doesn't matter where the couple's located. It's 30. We never multiply the couple by a distance when we're taking the sum of moments around a point. To find the moment contribution of a force, it's the force times the distance, or it's r cross f. But a couple is already a distance times a force. It just is 30. What we do need to include, though, is this 30 going to be positive or negative around point A? Right, it's negative because the couple is going to be going in the clockwise direction. It doesn't matter if this 30 was here, or at A, or at B. It would look exactly the same in this moment calculation. It just is 30, negative 30. So it's a force times a distance, force times a distance, force times a distance. This already is a couple. So conveniently, again, the benefit of choosing point A to take the moment about is now if I look at equation 3, there's only one unknown in equation 3, so I can solve it. So TBC is going to be 34.6. This is in kilonewton meters. This is in kilonewtons. So this is going to be in kilonewtons. I'll say it again. Equation 3, I could have chosen any point to take the moment about, point B, point C. But if I chose, again, point C, I would have had TBC, AX, and AY in equation number 3. It's still a solvable system. It's just harder by hand to solve it. But I would still get the exact same answers in the end. I would still find that TBC was 34.6 kilonewtons. This is positive, meaning that this is in tension, which it's a cable, it has to be, or it's a rope. Now that I know TBC, I can now use this information in equation number 1. I can now say TBC I know is 34.6. So now in equation 1, my only unknown is AX. Solving it for AX, I get 20.8 kilonewtons. My assumption up front is that AX was pointing to the right. Again, I really only assume that because that's the direction of my x-axis. But this positive value on AX means that assumption was correct. So this does point to the right. With reactions for pins, this does not mean tension or compression. This just means my assumption was right or my assumption was wrong. So this is the inference we need to make. It does point to the right. No matter what our assumption was, this pointing to the right would be the same, whether we assumed it was to the right or assumed it was to the left. If we assumed AX was pointing to the left, we would have gotten a negative 20.8 here, and that's the same thing. We assumed left, the negative would have told us that assumption was wrong. It was actually to the right. So this is globally true. It doesn't depend on your assumption. Again, we know TBC. I can now plug it into my equation 2, and I can solve for AY. AY, 87.7. It's a positive value. I assumed it was up. The positive tells me that that assumption was correct. It should be pointing up.